Welcome, everyone. How are you feeling? Good? Tired? Yeah, after a full day of sessions? Well, luckily for you, this is going to be a really light and easygoing session. No, I'm just kidding. This, this is going to be really intense, lots of technical information. So I guess that's why they put it at this hour of the day. So let's get going, and I hope you all have coffee and sugar handy, to keep you awake. All right, so welcome. My name is Enrico Campidoglio. I am a freelancer. This is me freelancing from home. Where I do programming, I'm a programmer, and I also do a fair bit of training, but that training I don't do from home. I actually travel to the places. But we are not here to talk about this or my hair. We are here to talk about Git. Now, is there anyone here who thinks that Git is hard? Okay, I thought more people will think that Git is hard. Well, I think that Git is hard. And I often wonder why. Why is Git so damn hard? Doesn't seem like it has to be that way. So I don't know if you ever Googled for why is Git hard, but I did. And surprisingly huge amount of results where people kind of complaints, rants, and says, why does it have to be so hard? And this was the beginning of my journey to understand how Git really works. So, at the end you see, yeah, Git is a nightmare. But then you see this. Why is Git good? And that's where it piqued my interest and say, okay, so someone actually thinks that this is worth it. So the question became, Git, what are you? So this is what I want to understand, and this is what I want to show you today. So what do you do when you want to understand something, the essence? You find the XKCD comic for it. And this is the one for Git. So here it is. This is Git. It tracks work on projects, and it does it through a beautiful distributed graph theory tree model. I say, okay, so how do you use it? No idea. You just memorize a couple of commands, and if everything goes bad, you delete everything and recover from a backup. Not really what I was expecting. So that's not very useful. However, if you read this again, there is actually a nugget of truth. A beautiful distributed graph theory tree model. This is worth investigating. So my next question was, okay then, what's a tree? So where do you go to find the definition of different words? You go to Wikipedia. But then I was like, wait a minute. Not that tree. So then I clicked on that link and I ended up here. Tree in the graph theory. So a tree is an undirected graph where any two nodes are connected by exactly one path. Okay, now we have something we can work with. Now, have you done git log sometime? Yes. Then you know that when you do git log, the history of Git looks like this, where each one of those boxes is a commit. So it's a sequence of commits. Those commits are interlinked, and at the end of a line of commits, there is a named reference, which is the name of your branch. Now, you can have, of course, more branches. Now, this looks a lot like a bunch of nodes that are interconnected, just like Wikipedia said. So yes, this is a graph. Now, let's consider the second part of the question. of the definition. And that was, in order to be a tree, there must be only one path between any two nodes. Now, look at that graph and choose any two nodes and try to find how many ways can you go from one to the other. For example, from this to this, how many ways are there? One. What about from this to this? How many ways are there to reach one from the other? Still one. So yeah, there are no circular references. So yes, absolutely, this is a tree. So you started to see that the XKCD comic actually was telling the truth, that Git is a tree, but not an undirected tree, because an undirected tree means that any two nodes know about each other, which in Git we know that that's not true. That's not true because in Git you can only go backwards in history. A commit only knows about its parent. A commit doesn't know how many commits come after it. So it's not an undirected tree, it's a directed tree. So now we have something, we have a metaphor to think about how the history of Git looks like. The history of a Git repository is a bunch of nodes interconnected where you can only go backwards from any node. Okay, let's unpack one of those nodes. What's in a commit then? In a commit, I don't know if you ever looked under a commit. Have you ever lifted a commit and looked under? If you had done that sometimes, you will find that under a commit, there is a representation of the root of your project. The root directory of your project is referenced by a commit. And Git calls those things trees. Not the same as the tree we've been looking at. So a great example of how programmers use the same term to mean different things. So a directory is a tree, yes. Under the tree, there are eventually your project files. Git calls them blobs. All right. A commit also has a reference to another commit, which is the parent, which also has a tree and a bunch of blobs. And of course, at the end, you have the branch. Now, this is the essence of this is all there is to Git. There is actually nothing more than this. These are all the objects that you are using when you are using Git. However, you don't know them in this form, you probably know them in this form. You've probably all seen these long strings of characters and numbers. Those are the ways in which Git identifies those objects. So a commit is identified by a string that looks like that. But what is it? It's the hash of the content of that object. The SHA1 hash. Or if you are into the whole Git community groove, you say the SHA. It's the SHA. Okay, so of course for files, it's easy. If you hash the content of a file, you get a SHA. For directories, how could you hash a directory? You hash the path of the directory. So then you get another SHA. But what about the commit? What's in a commit that you can possibly hash? That's what we are going to find out. So let's take a look behind the scenes of a commit. Now, how is the font? Is it big enough? Can you read this? You have to tell me now, because then once I get going, I don't want to change sizes. Is it okay? Okay. So what I have here is a directory. It's a project. On the left, I have a command prompt, which is currently in that same directory. And on the left, you have sorry, my left is your right, and your right is my left. So let's all keep that in mind. On my right or left is the file system view of that project. So that is the project we'll be looking at. And what will we be doing? We will be creating a commit, the first commit in this project, from the ground up. We will be building all those blocks that I've been showing you, blobs, trees, commit, branch, from the bottom up, to see if what I have been telling you is true or not. And that will give you an understanding of how Git actually works. So this is not even a repository yet. This is just a project, and the code doesn't really matter, but this is an embarrassing program that I just use as an example. It's not even a calculator. It tells you that it's a calculator, but it's not. So what is the first thing you need to do? You need to initialize this directory as a Git repo. So you say git init. And watch what happens. A directory appears called .git. Let's see what's inside. Now, this is where Git stores all of those objects that I've been telling you about. The trees, the blobs, the commits. How does Git store them? It stores them as files, just like your files, because that is all it can do. There is only ever files and folders. Where does it store them? It stores them in objects. But right now, you see that it's pretty empty. What about the branches, those references that I've been telling you about? They go under refs. And that's also pretty empty. Nothing there. Okay, so let's start out by telling Git that we want to commit this calculator file from the ground up. Now, remember when I told you that Git identifies those objects by doing the hash of its contents? Everything is hashed. So the first thing you do is that you tell Git, okay, hash this object that this file that I'll be giving you now. And Git says, okay, here is the hash, the SHA of that file's contents. But you still see that there is nothing here. Now remember that Git has been created by a bunch of programmers. Many programmers. Well, it was created by Linus Torvalds first, but he made 4 programs. That was the totality of Git. Then he handed it off to a community, and they built upon it. So remember, it's programmers. So when you just say hash object, that's what you get. You get the hash. Git doesn't store anything yet. You have to say hash object, right, and then Git stores the file in its own object database. Now, if you have had enough caffeine, you might notice that this file is smaller than this one. So that makes me think, okay, let's have a look at what that file actually contains. Oh, and by the way, you see that the hash, the first 2 characters become the name of the directory, and the rest becomes the name of the file name. So, actually I forgot to copy this in my clipboard, so we can reference it later. All right, so let's take a look at that file. So in the Git directory, we say objects 5D. What's inside there? Garbage. Now this is actually the zipped content of your calculator file, because Git, that's why it's smaller. Git zips everything. So how can you look at it? Well, you need to use another command. These commands that I've been using now, those go under the term plumbing commands. Those are the low-level commands that Git uses when you use your high-level commands. git add, git commit. Those are high-level commands. They're called porcelain. Those in turn interact with a bunch of low-level commands, which are called plumbing. You will never ever use those, but those serve as a nice teaching tool. So cat file, print, and now you can just give it the SHA because Git knows how to find it. And there is your file. Okay, so we're getting somewhere. So now you see here, we have created a blob. Now the next step is to create a tree. Now it turns out that if you just save a file in Git object directory like this, it doesn't mean that Git will track it. If you want that Git tracks the content of your file in your working directory, I mean the file here, you need to tell Git about its path. So what Git does is that Git has an index, which is exactly what it sounds like for once. It's an index of all the paths of all the files that Git is tracking. So in order to track a file, you need to tell Git to update its index, and you want to add. Now you might wonder, why didn't they make a command called add index? Why update index and then add? No good reason. So you say add a new entry to the index, and then you need to say, okay, what kind of file is it? Is it a text file? Can you read it? Can you write it? Is it a shell script that you can execute? So no, you need to tell it that it's a regular text file, which obviously that's how you do it. This is a regular text file. Okay, then Git needs to know, okay, what's the SHA of the file's contents? What's the SHA of the blob? Well, here it is. And the last and most important part is, what is the path of this file that you want me to track? And you say, okay, that's it. Ooh, new file appears. That's the index. It wasn't there before. Now, as soon as I see a file in the .git directory, I get curious and I say, okay, what's in there? Binary. So the Git, you can imagine a project like the Linux kernel, how many files there are. And those all have an entry in the index. So index with potentially thousands and hundreds of thousands, millions of entries in that. So you one does not simply store such a huge file as a text file. You store it in some binary format. So that's what it is. So, but you can look at it. You just need to use the right low-level command. So you say list files stage. And this is the content of your index. You see exactly one file, which is a read-write. Here is the SHA of the blob. Here is the path. And what about this? Since I only have 1 hour, I can't get too much into that 0 there. But there is a whole story of what that means. So if you want to know, just find me afterwards. I'll be here until late this evening because my flight is late. So if you want to know what it is, I'll explain you afterwards. For now, you just will have to keep wondering. So now we have an entry in the index. Turns out that in order to create trees, in order to create a representation of directories, Git, all it has to know is the path of the files from the index. Because given that it knows the path, it can automatically parse them and determine in what directory those files are, the whole way up to the root. So it can parse them and create a tree for every directory. So now that you have an index, you can simply say, Git write the tree. And you see two new objects appeared. Why 2? Let's find out. So first, let's check what this is. What is that blob? If you want to know what kind of object a SHA points to, you ask cat file, give me the type. It's a tree. Okay. So then we can say list tree. Show me the contents of that tree. Sure. Inside that tree, there is another tree, which represents the source directory. So the tree we got back is the tree that represents the root of the project, right? And from there, there is another tree, which is the source directory. And underneath that, if we looked at that one, what is in that tree, you might guess what there is there. There is a blob, and that's our file. Okay? So now we have actually started tracking things. However, if we do git log now, oh, there are no commits yet. Why? Well, we haven't made a commit. We have just created blobs, one blob and two trees. So we need to create a commit, which is also an object. And that was the question when I started this demo. What the heck is in a commit? We'll find out now. So now that we have a SHA of a tree, we can say commit tree. Here is the SHA of the root, right? Hopefully it's the root. Let me just double check, because if I make a misstep here, we need to delete everything and start over. Let me see what's in that. Yeah, that was the root. Okay, commit tree. Here we go. Let's give it a message. Add the calculator. New object. Starts with 2b. How big is that file? 141 bytes. What can possibly be in a commit? Well, let's find out. Cat file. Print the content of that object that you have there. Okay. So in a commit, there is only metadata. There is only information about the change. You see that a commit points to a tree, and that's our tree, the root of the object of the project. Then it has information about the author and the committer. And why are there two? Why do you have two fields for what usually is the same person? Well, when Git was created, it was created to handle the history of the Linux kernel. Now, in projects like the Linux kernel, one does not simply walk in and commit to the source tree. You can submit a patch, you can be the author of a change, but someone else, which is a trusted person on the Linux team, is gonna check it and say, yes, I testify that this change is good, and I am the committer of the change, but I'm not the author. That's why you have two fields. And that's because you want accountability. Who made the change and who actually approved it? Now, many times, they will be the same for most projects. However, if you are in an open source project and you make a pull request, you could argue that sometimes this happens, that you are the author and whoever merged the pull request is the committer. So it turns out that it's useful. What about this? What's that number? Any guesses? Yeah, time. That's the timestamp, but why does it look like that? Well, it turns out that if you are, like me, a Unix nerd, you like to think of time not as a hour, minute, second. You like of thinking of time as the number of seconds that have passed since January 1st, 1970. So when someone asks me the time, I always ramble a number like this. And then they go like, yeah, this is the number of seconds since January 1st, 1970. And if you want to know the real, the human version of that, you just can convert it into another format. Now you may wonder, that number will keep increasing. It will never stop increasing. So, How do you store that number? Any guesses? This is apparently stored here. And all Unix tools, imagine a database where you have a data type of type datetime. It's also stored as a number. So how do you store this number? Well, if you are a programmer in the 70s, you think that a signed integer of 32-bit will be plenty. It turns out that we will be running out of space in a 32-bit space, the amount of information you can represent in 32 bits signed, that means it includes the minus. We will run out, and I'm sorry to know that you are going to find out this way, but on January 19, 2038, we will overflow that 32-bit integer, which means that the next second it will go back to minus 2 million, whatever is on the other end of 32-bit max number, which translates to December 13, 1901. So yeah, this is called the 2038 problem, and it's a different flavor of the famous Y2K problem. So some system will crash, and in my research I already found out that NASA lost a satellite, not because of this exact problem, but because the programmers who made the software decided to store the time as a number of seconds from January 1st, 2000. Then that number overflowed, and the systems on the satellite kept restarting themselves, cutting off communication from Earth. And the latest report is that NASA gave up trying to re-establish contact with that satellite. It's lost because of one such problem. All right, 2038. It's a while, so we don't have to worry about it now. So where were we? Yeah, we were looking at the commit, which contains this information, and of course it contains the message. So that's what's being hashed. And if you count that the datetime and the author and the message is part of the content that's being hashed, now you know, if you ever heard don't ever rebase, have you heard that? Don't you ever rebase if you have pushed your commits? Have you heard that? Then you'll be wondering, why is it so important? Why can't I rebase once I've pushed my commit? Because if you rebase, you are going to change one or more of these values, for example, the timestamp. That will generate a new hash, which means that the same commit pointing to the same tree is going to have a different hash, a different ID. So whoever pulls it later, Git is going to think that it's a new commit, but it's the same as before. So you have a clone. You have two commits pointing to the same changes. And that's bad. So now we have a commit. Do we have a history? No, still no history. What are we missing? We have the blobs, we have the trees, we have the commit. What we don't have is the branch. Let me see if I have the commit. No, I have the epoch. Let me just copy the commit hash in my clipboard. So what we need is we need to update the master branch reference so that it points to this commit. How do you do that? You say update ref, refs, heads. We know that the branches go under here, master, and the SHA of the commit. Now we have a history. Now, are you all with me? Yeah, are you all awake? Yeah, good. So, was it exciting? Not that much. I know. But now I'm going to do something exciting. I'm going to make a commit using the regular commands, the ones that we've been using all day, every day. So let's start by making a change to this calculator. And what you want to change? Something easy. Let's remove this useful comment. So now I made a change. I removed that line, okay? Now I'm gonna say git add, and now watch what happens here, of course. You know what happens when I say add. Hash the blobs, add to the index, create a tree, but not a commit. So then I say git commit, removes a useful comment. Now you see a bunch of whole new objects here. So now let's do a git log. We have 2 commits. Let's look at this one, which is the latest one that master is pointing to. You see that the master reference is being updated to whatever is the latest commit. Let's take a look at the latest one. There is, if you've been paying attention, you see that there is 1 extra field now compared to before. Here you have the reference to the parent commit and nothing more, which of course it's our famous hash from before. This is also another reason if you rebase, you're gonna change the parent. And if you change the parent, you get a new hash. And this happens as a domino effect. If you change 1 hash, all the descendants change. So you see why this is potentially a problem. So, but this is not all. Let's take a look at the tree that it's pointing to. Of course, it's a different tree because the file is different. Let's do a list tree recursively so we get all the way to the blobs without going through the middle directory. Now, this is the blob over. So the commit we did together is this, the parent one. The commit I did now is this. This is the blob that's being referenced by the latest commit. What do you expect to see? Do you have any expectations if we look at the blob that's being referenced by the latest? We just changed 1 line, right? What do you expect to see? The change? Well, let's look at it. It's the entire file. So every commit is pointing to a copy of everything, okay? Which means that when you say, show me the difference between the files referenced by the commit referenced by master -1, this is a syntax that means from whatever commit is being referenced by master, go back 1 step, the parent. You can only go backwards. So you can say 1 parent, 2 parents, 3 parents, and go back. So show me the difference between the parent of master and master, and it shows you, yeah, you remove that. What if I invert them? You see that the diffs are being generated on the fly because Git has the entire files under every commit. Now you may think, but hey, wait a minute. That sounds incredibly wasteful. Imagine a project with many files, thousands of files. A copy for every commit sounds like a lot. It turns out that Git is smarter than this. So you see all of these are the blobs and the trees, the copies of everything. Once you reach a certain size, which by the way you can find out, you can say count objects. How many objects are there in my Git repo? There are 8, which you can count them, trees and blobs and commits. And they occupy a total of 32 kilobytes. Okay, you can tell Git, I want you to optimize this. You have all the files. You know how they changed. So instead of storing a copy of every file for every commit, what about you take a sequence of commits and you calculate the differences between them and just store the differences. It's called the delta chain. This happens automatically, so you don't have to worry about it. But if you run such a command, like repack. If you watch this now, what happens? They have all gone. And where have they gone? They have gone into this so-called pack file. Now, this happens regularly in your repository, so you don't have to worry about it. However, if you are leaving this session and have a burning question of knowing how many packs are in my project, you can say git count objects, give me the human version, and give me the summary. Oh, give me the verbose. Sorry. Even I forget those. Git will tell you, now there are 0 objects in your database, which is true. There is none left here, but there is 1 pack, and inside that pack there are 8 objects, which were the 8 that were outside the pack before. Now they are in the pack. All right. Maybe that was exciting. Or maybe not. So this means that what is Git? Was the question I had at the beginning. What is Git? Git then is a snapshot machine. It's a snapshot machine with a set of commands that together form a domain-specific language. You can think of all the commands that I've been using as a sort of programming language. You see, we are directly manipulating those objects. But how does Git store those objects? It stores them as files. So you can say that Git is a content tracker. And in fact, if you look at the manual page of Git, it even says it right on the first line. Git is the stupid content tracker. Why is it stupid? Because it's embarrassingly simple. I showed you in 25 minutes, that's all there is to it. Every time you commit, that's what happens. So it's a content tracker, but as I told you, it saves everything as files. So maybe it's a file system. And if you look it up, you'll see that Git is often called, it goes under the category of a virtual file system, which is a file system built on top of your real file system. It has its own abstractions, which are blobs and trees. But how does Git reference those objects? With the shas. So what is Git really if you go down one more level? It's a hash table. Git is a hash table, just like JavaScript. Any JavaScript programmers? No. Whew. I always try, and then I try to run. So yeah, Git is a hash table. It's a hash table where you have a bunch of hashes that point to objects. This is the mental model you can keep when you're working with Git. This removes all this complexity, because you know that underneath, that's all there is to it, and every commit has a snapshot of everything. So at this point, you might wonder, okay, that sounds cool, but no. What does that do for me when I sit there and try to commit something or resolve a problem? Well, having this mental model in mind helps you first, when you search for solutions, you will see this terminology being used. And having this mental model that this is actually all there is to it, you have a reference point to go back to when someone in some forum explains what something does in Git. Not only that. Someone once said, keep your own history readable. Now, some people, they do it by, thinking everything ahead and not making any mistake. The rest of us, we work the way we work, and then we use tools like Git Rebase, to go back and modify this graph of objects, the history. We move things around, remove commits, squash commits together, so that we create a readable history. Now, what strikes me here, of course, this was Linus Torvalds who said that. What strikes me here, was that making mistakes and readable history. If you have ever used a source control system before Git, you know that source control systems have been pretty unforgiving. You make a mistake, you commit, that's it. Everybody is going to see that. Have you ever made a check-in where you forgot the project file? Yeah, you had a bunch of new files, but you forgot to include the project file. It's like sending an email and telling, look, find the attachment, and then sending another email afterwards. Oh, by the way, here is the attachment. That's the same thing. So you make another check-in and says, oops, forgot the project file. That's not if given enough of these mistakes, which of course happen, they clutter the history. So we want to be able to make mistakes and fix them to keep the history readable. So don't expose your crap. That's also a quote by Linus Torvalds. That's what this message is. So what is the reason why you should keep this mental model and understand how Git works? Because of two reasons. One, that gives you the freedom of workflow. That means you can work any way you like. If you like to make small commits often and then go back and squash them, you can do that. If you want to make fewer commits and commit maybe once in a while, you can do that. If you want to work in many branches, because you have seen what a branch is just a reference to a certain commit. You can create and delete branches as easily as you can remove one file, which points to a hash, right? So branches are cheap. You can use them to your own advantage. So freedom of workflow, while also not exposing your personal workflow in the history that is shared with everybody on the team and future generations of programmers. An example, just to give you an idea of what you can do. So here is this is a Git in the browser. So it's not the real Git, but they implemented the Git commands in a web page using JavaScript. Yeah. But that doesn't really matter because it's useful as a way of an example. So here is you recognize this model, right? You will find it everywhere. This is a commit with a reference, with a branch reference called master, and head is another reference that points to whatever you have in your working directory. When you say checkout, you are taking the contents of a snapshot and putting them into your working directory, and head is keeping track of what commit is this working directory coming from, which snapshot does it map to. So let's make a new commit where I say git commit B. Actually, let's give them some interesting. No, let's not do that. Let's say A, B, and C. You see, we are creating the graph that we have been working with. Okay, now this is the master branch. So that's where I usually try out my ideas, stuff that I don't know if it will ever work. I do it in master. Why? Because I have the freedom of workflow. This is just on my machine. Now I suddenly realize, this is getting too far with the ideas. I better create a branch for it. Now, if this was another source control system, good luck, no way. But with Git, I just say, okay, let's create a new branch right where I am now on this D commit, and let's call it experiment. New branch means creating a new reference to the same commit, right? So then I can go back and say, with this master, let's move it back. And you need to say hard because then you really mean it. Like I really want you to do it now, and I want you to move the master branch back 1, 2, let's say 2. So from master back 2. Remember, 1 parent, 2 parent. So now master is a reference. I just change it. It points to a different commit. Now a bug report comes in, which is something that must be fixed ASAP. So I'm in the master branch. I fix the bug. So I say bug fix. So the master branch has moved. My experimental work is in a separate branch. All right. Now I want to resume work. So I check out my experiment branch. Now watch what head does. I just move head to that, which means the files that are in the snapshot of D are now in my working directory. Now I can keep on working, but you know what? I actually want that bug fix in my experiment branch. I want to include it. So what do? I rebase my experiment branch on top of master, which means, what does rebase mean in this context? Means that this branch, experiment, I want to change its base from this to this. Because if you go back, between experiment and master, what is their first common parent? It's B. So what rebase does is that it removes those two, applies master, and replaces those two. I know, lots of words, it's better if I show you. Git rebase on top of master. So now you have seen that my C and D are now appearing after the bug fix. And the old ones are being left behind. Those are objects that are in the database, but they are no longer referenced by anything, which means Git will eventually delete them. Because yes, Git has a garbage collector. But then at this point, I want to say, you know what? I don't want history to look like this, because it looks like I did the bug fix before I did C and D, which is not what happened, right? So I regret this immediately. So I do reset, hard of course, and then I say, what do I reset to? In reality, I don't see those, right? I see them now because I have a graphical tool, but in a repository, you don't know what they were. So I need a way to say, okay, move my experiment branch to whatever it was pointing to before now, before my latest operation. Okay. Then I say, the one before now. Okay. So let's move it back. Oh, I need to say the reference, git reset our experiment at 1. So now I'm moving back to where it was. Now I want to apply the bug fix on top of experiment. So I say git cherry pick whatever commit is referenced by master. So I apply it over there. I'm manipulating this graph of objects by using the domain-specific language. Now I will give you this, and I won't hide it. Those commands make no sense. And that's the problem with Git. When you look for why is Git hard, what everybody means is not why. So of course, they may or may not know that it's actually easy at the object model level. But the first thing you see is not this graph. What you see are the commands, and the commands are cryptic. The options are cryptic, the names are strange. What's a rebase? What's a cherry pick? Why reset hard? And why not soft? There is a reset soft. And what is between soft and hard? There is also a third mode. Can you guess? Mixed. You can do a git reset mixed. So the problem with Git are the commands, which make no sense. And the reason for that is Git is made by programmers. There is no other reason why it should be that way. So if we can remember one thing from this whole session, actually it's 3 things. So Git is a content tracker. It only tracks your files with its own object model, which is extremely simple. Do not ask yourself what you can do for Git. Instead, ask what Git can do for you. By that I mean, instead of trying to learn everything that you can do, or what Git can do, instead decide first how you want to work. or first at the individual level, but also within your team. What's your branching strategy? How many branches do you want to keep? Do you want to work with feature branches or not? Do you want to have just one main branch where everybody commits to? Or do you want to have two branches, one stable master and one next version called develop or something like that? So choose how you want to work and then find the commands that you need to use to achieve that. And the third is keep a clean history, because with Git, you actually have a good shot at doing it. If you want to know more about what you can do with Git, I have a Pluralsight course called Advanced Git Tips and Tricks. So this obviously assumes that you have some experience with Git, but what I've shown you today is also in that course at the beginning. So that's it for this shameless plug. And with that, I want to say thank you.